Good day, everyone. In previous video, we learned that there were three Newton's laws of motion: the law of inertia, the law of acceleration, and the law of interaction. The law of inertia says that the net external force of an object is equal to zero, which means there is no unbalanced force on that object. Hence, the acceleration must be zero. And there are two situations where the acceleration is zero. It can be at rest position or moving at a constant speed. Meaning, the particle undergoes rest position or maybe in motion with constant velocity. And we call that as equilibrium. It can be static equilibrium or a dynamic equilibrium. Both of them, the acceleration is zero because the net external force is equal to zero. In second law, says that whenever there is a net external force on any object, that external force is proportional to the acceleration. It is directly proportional to the acceleration, which means that the greater the acceleration, the greater the force, vice versa, meaning the greater the force, the greater the acceleration. And according to second law also, that the direction of that force is the same as the direction of the acceleration, which means if we know the direction of acceleration, then we can trace the direction of the unbalanced force. In second law also says that the acceleration is inversely proportional to the mass, meaning the greater the mass, the smaller the acceleration, but the smaller the mass, the greater the acceleration. And the second law is very important if we are solving problems in dynamics in our everyday life. Now the third law says that for every action, there's always opposite equal amount of reaction, which means that the two forces are coupled. They cannot separate each other. Meaning, if you apply a force on the object, then the object applies a force on you with the same amount. Meaning, in return, the object will apply you with the same amount of force, but in opposite direction. Now, that three laws are very much important in solving problems in dynamics. Now, in order to use the formula or the laws of Newton's, we badly need the so-called free body diagram. So we learned that in our previous topic, that the free body diagram is a diagram showing all forces on the particle. Which means that in order to apply the Newton's laws of motions, we should know what are the forces acting on the particle. Meaning we have to show all the forces on that particle, and we call that as the free body diagram. Meaning if you miss one force on the object, then we cannot say that it is a free body diagram. So we have to be careful in analyzing all those forces on the object. The forces should be reflected on your diagram, and that diagram can be used in order to find the net external force. Remember that if we know the net external force, then we can solve for the acceleration because we have the formula of second law of Newton. Okay? Another thing is, in order to apply or solve problems in everyday life, friction must be understood. Now, remember friction, in our previous video, we learned that it is always a force between contact. Meaning, if one object interact to the other object, if there is a contact between them, then there is always a friction. And that friction is proportional to the coefficient of friction. The coefficient of friction is the property of two materials in contact and the ability to conduct the friction. So, for example, we have the wood on the glass. Then, there must be a coefficient of friction on that condition. And that coefficient of friction is different to different materials. Meaning if we have wood and wood, then there is another coefficient of friction. And the coefficient of friction, again, is proportional to the force. The greater the coefficient of friction, the greater the frictional force. Now, the coefficient of friction is it is because of the normal force. If you have the normal force and you have the coefficient of friction, then we have always the frictional force. Whenever there's a contact, there is always a force of friction. And friction is an opposing force due to motion. It is always against your motion of the body. So it is always a counter force. That's why it is heavier to pull up the object in an inclined plane. Why? Because of its friction and also the gravitational force. When you push an object in horizontal surface, then you are actually applying or neutralizing the amount of friction. In order to move that object, you have to overcome the friction. And that friction, again, depends on the coefficient of friction and its normal force. In fact, to obtain mathematically the frictional force, it is the product of the coefficient of friction and the normal force. Now, in this video, we will study the Atwood machine. This is one of the many applications of Newton's laws of motion. And this belongs to the dynamics of motion, answering why object moves. Okay? Now, if we consider a frictionless pulley, meaning a pulley is a kind of device that will rotate. We have an axle between the wheel. So if we can ignore that friction, or there's a friction but it's in minimal amount, then we can use it and let that be fixed on a certain height. It should be elevated. And if we have two objects, mass A and mass B, and connected by means of a rope or any or string, then we call this as the Atwood machine. Now we call this as an Atwood machine. Now, Atwood machine is invented in 1784 by George Atwood, from the word Atwood, because George Atwood invented the Atwood machine. And this is used to verify the mechanical laws of motion with constant acceleration. So this is a good demonstration in discussing the constant acceleration, the uniformly accelerated body, because it provides a constant acceleration. Okay, take note that we can call it as an Atwood machine if we can ignore the frictional force on the pulley, and the string in contact with the pulley has also approximately equal to 0, meaning we can ignore for simplicity. Now, this illustrates the principle of classical mechanics. This is the common material used for demonstration, the Atwood machine. Now, if we have this object, mass A and mass B. Now, suppose mass A is less than mass B, meaning it's a smaller value in our mass with mass B. Now, if we release it, then surely mass A will be moved upward, while mass B should be moved downward. Why? Because of its gravitational force. Now, since mass A is connected by means of a string, then the mass A was pulled by mass B. And take note, the mass provides the gravitational force. And that gravitational force is the product of the mass times the gravitational acceleration. So the acceleration of A must be upward, and there must be an acceleration also of B, which is downward. Take note that the acceleration of A is always equal to the acceleration of B, vice versa. So the acceleration can be any number, no? But if we have in that case, then the acceleration is not equal to 0. Why? Because there is a motion. motion occur, and it comes from rest and release, then therefore surely the acceleration is not equal to zero. And remember that in second law, the acceleration is proportional to the unbalanced force. Hence, the unbalanced force also is not equal to zero. Again, remember that the unbalanced force is the net external force on the object. Meaning, in mass A, there is always an unbalanced force. In mass B, there is also another unbalanced force. Now, in that case, both of them, the unbalanced force is not equal to zero. It's because there is an acceleration to the objects. Right? Okay? Now, what will happen if we have mass A greater than B? Mass A has a greater amount of mass compared to B. So therefore, surely that mass B will move downward and mass B is upward. Mass B will be pulled by mass A. So if we release it, then again mass A will move downward with acceleration and mass B will move upward with acceleration. But take note, again, whatever the acceleration of A, mass B or mass A should have the same acceleration of mass B because they are connected by means of string. And the acceleration is not equal zero. Again, the net external force both of the object is not also equal to zero. There must be an acceleration. If there must be a force. If there's a force on that object, net force, then there's always an acceleration, vice versa, as second law Newton says. Now, what will happen if mass A is equal to mass B? Then, if you release it, it won't move. It is in a rest condition. Hence, the acceleration is zero. Because the moment the object is at rest, there's no acceleration. And remember that acceleration is a change in velocity. So, both of them have zero velocity. So, there's no change to the objects. There's no initial, there's no final. So, the acceleration is zero. It's at rest. It can be, meaning if the acceleration, the unbalanced force is also equal to zero. But if this is at rest, take note, because they have the same amount of mass, meaning they must have the same amount of gravitational force. And remember that the gravitational force is the force that the Earth exerts on that object. And it is the product of the mass itself by the gravitational acceleration. Okay, this is at rest. But if we apply just a very, very small force applied to the object, then the system will move, but in constant velocity. Meaning, it undergoes uniform motion because the acceleration is zero. Whether if you apply a force on that, the acceleration is equal to zero because they have the same mass and they have the same gravitational force. Now, if we apply to the opposite side by a very small, just let the object to move, then the object will move at a constant speed. Whether you apply it hard force, then there is a situation that velocity have the same value. Why? Because they have the same mass. That's ideal. That's the ideal situation, provided that the friction between the string and the friction of the wheel or the pulley must be neglected or can be neglected. No, therefore we call this as uniform motion or constant velocity. Now, our task is to compute what is the acceleration of the system in an Atwood machine. These are common problem. Remember that the acceleration is very much important. In dynamics, we should know the acceleration. Why? Because the acceleration involves unbalance, of course. And the acceleration also involves the velocity. Remember, in kinematics, acceleration can provide the velocity, and the acceleration can provide position. And the acceleration can provide also the time. So it describes the motion of the particle. So, in other words, for every problem you encountered in the application of Newton's law, the acceleration is the center point of the physical quantities that should be determined. We should know the acceleration. The reason is, so that we can apply the formulas for the uniformly accelerated body. Okay, so the task of this is to calculate or provide a relation of the acceleration. And maybe you will be asked how much tension in the rope or string experienced because of that configuration. It was attached on A, mass A attached to B. So those are questions that we need to answer. Okay, to answer this is to assume first that mass A is less than B or vice versa. So take note that if A is less than B, then A should be moved upward while B should be moved downward. And A, while moving upward, has the unbalanced force and call that as summation of forces A. So summation of forces means it is the net external force of A or the resultant of A or the unbalanced force of A. Terms are the same. Okay? Hence, A moves upward, then B should be moved downward. And since B has the acceleration which is the same to A, then it has the net external force on B also. Now remember that the acceleration of A is the same as the acceleration of B, but the net external force of A is not equal to the net external force of mass B. They will have the same unbalanced force if they have the same mass. Now in this case, their unbalanced force must not be the same. Okay? So now, in order to find the acceleration of the object again, because our task is to solve for acceleration, to provide a mathematical relation, all you need to do is to overlay a Cartesian. Why we need to overlay the Cartesian? Remember, in our previous understanding, that the dynamics of motion, applying the second law of Newton, it requires free body diagram. We cannot solve the problem in dynamics without understanding the free body diagram. Because in a free body diagram, it is where that we can provide mathematically the net external force. And take note that net external force is very much important to apply if we apply the second law of Newton. Okay? Now you notice that the Cartesian, I overlay the Cartesian where the upward axis assigned to be positive x. That's my strategy of solving. Meaning, with that, I assign upward to be positive x to ensure that the net external force is towards up. Because according to that situation, when A is less than B, then surely mass A will move upward. So if the mass A will move upward, then it follows that the net external force should be upward also. Okay? Remember that whatever the direction of A is the same direction of the unbalanced force. So I assign positive x in order to ensure that if I take summation of forces along x-axis, then the result should be the net external force on that object. Okay, that's the reason. So meaning, upward positive x, downward is negative x. Don't worry with the horizontal axis. I assign that y because there's no, in this problem, there's no forces on the y-axis. Hence, we will focus only on the x-axis or the vertical axis. Now, what are the forces on mass A? We should indicate all the forces. You have to indicate the forces that acts on mass A. So if you analyze it, mass A, take note that if you have the mass, you have the gravitational force. And take note, gravitational force is a force that acts on the object because it is the earth exert on that object. So your weight, the weight of the object is one of the force that acts on the mass A. And take note, it is negative. Why? Because upward is positive and gravitational force is always vertically downward. So it should be negative. And remember that the weight is the product of the mass times the gravitational acceleration. The mass is mass A multiply it by the gravitational acceleration, it is already a weight. Meaning, there's no problem as the weight is concerned. We know how much is the weight. We just multiply the mass by the acceleration. It is just like multiplying the mass and acceleration due to gravity. It's just the formula of second law. No? If we use the acceleration due to gravity, 9.8, multiply by the mass, then you are calculating the gravitational force. Okay? Another force on A is the tension in the cord. T corresponds to the tension. Now take note that we connect the mass A with a string or rope. So it applies an upward force. So the application of string is a tensile force. It is tend to pulled up. And it is the reason why mass A moves upward because of that tension. It is the tensile force. Okay. So if you analyze clearly the object, there's no other force other than that. We have only two, the weight and the tension for now. Now, in case there's a contact between object, then you have to add the frictional force. But in that case, it was hung. So there were only two forces. Okay, then because in this problem we should construct two free body diagrams. Now, in dynamics of motion problem, the number of particles in motion in a system are the number of the free body diagram that you should construct, because you can use it in order to solve the problem. Now take note that in you look at the free body diagram in mass A, we can calculate the weight, diba? Because we have the mass and we have the gravitational acceleration. We don't know the T. We don't know how much is T, and we don't know the acceleration. Hence, we don't know what is the unbalanced force. So in that case, there were two variables, possible two variables, the acceleration and the tension, or maybe the net external force. So with that reason, we badly need to analyze the other object, which is mass B. So in that case, again, we will overlay another Cartesian plane. But take note, the strategy of overlaying the Cartesian in order to construct the free body diagram is to analyze where that object moves. So in that case, with that configuration that mass A is less than mass B, then mass B should be moved downward. Hence, our acceleration is downward. So with that, our Cartesian axis X should be downward. This is reverse to the mass A free body diagram. X is upward, but this one, X, I assign it to downward. Other books, other authors or solving this problem, there are different ways. For me, I use this one. Whenever the particle, you have to analyze the direction of the particle. Now, if you know the direction of the particle, if you're very sure that the particle will move that, or you're not sure, then you can assign. Then assign that as positive X. The reason is, by assigning positive X-axis downward, we let the net external force be equal to the sum of all forces along that axis. Okay, that's the simple strategy. Assigning X downward as to be our positive axis is to ensure that the net external force along X is always equal to the unbalanced force of mass A. Remember that we are needed the amount of the unbalanced force, because knowing the unbalanced force is to know the acceleration by using the second law of Newton. Okay, now what are the forces on mass B? So again, because we have the mass, we have the gravitational force, and it is always downward. So there you can notice that the gravitational force is now positive. Why? Because the axis is positive downward. Unlike of mass A, it is upward. So hence, weight is negative. So in this case, now remember that mass B also is in contact with the string, which means that there must be a tensile force that tends to move up. It moves up, but take note that B is moved downward. So therefore, Why? Because the weight dominates the tension in the cord. So therefore, the unbalanced force will cause the acceleration. So tensile force must be a negative because it is opposite to the axis, positive axis, x-axis. And there were again two forces acting on that object. Okay? So these are the free body diagrams. So if you arrange this, no, and these are the two free body diagrams, the free body diagram of A, the free body diagram of B, and they are very, very important in solving problems. Okay, now what next? Next is to use now the free body diagram and the second law simultaneously. No? So if we analyze the free body diagram of A, all you need to do is to sum up all forces. No? We have already the forces on the free body diagram of A. So all you need to do is to sum up all forces along X. Now remember that T is positive, so sum up algebraically, and the weight is negative. Okay? Then remember weight is the mass times the gravitational acceleration. So it should be what? It should be T minus ma times acceleration, and that is coming from the free body diagram, which means that without the free body diagram, then you cannot provide that relation. That relation says that the net external force, or the sum of the forces along X is equal to T minus ma times G. Okay? Now, remember that we can also sum up along Y, but in that case, no need to sum up. Why? Because there were no forces acting along Y-axis, so the sum is also zero. Meaning, there's no way that the particle will move both sides because there's no unbalanced force. The sum of Y is equal to zero. So the tendency of the object is whether to move upward or to move downward. Okay? So we need only the net external force along X. And we are very sure that the net external force, remember, is along X-axis. In fact, we set the axis upward to ensure that if you sum up all forces along X, then it is equal to the net external force of A. Okay? Now, using the second law of Newton, remember, second law of Newton is the product of the acceleration and the mass of the object. So meaning, the net external force using the second law is the mass A times the acceleration A. That's second law. Okay? So there are two definitions of the summation of forces. We have from the free body diagram and we have from the second law of Newton. Now, according to algebra, then both of them are equal, which means that the T minus mag is the same as the mass A times the acceleration A. So we can equate the two. Okay? Now, if you analyze that equation, we don't know the tension and we don't know A, which means that we cannot provide the solutions of that variable. Nothing to worry with A because mass is given and the acceleration is constant. So all we need to know is how much is A and how much is T. We don't know T, we don't know A. So leave this as equation 1. So this is the result of the equation, or this equation is the result from the free body diagram of mass A, and it provides two variables. So in order to solve problem, because in algebra, in order to solve two variables, we need two equations, and we have only one equation. So we need to find another equation, and that equation can be found in the free body diagram of mass A. It should be simultaneous, no? Because the equation is called to be simultaneous if they have the same variable present on the equation. Okay? So do it the same, no? For this time we will proceed to the free body diagram of mass B. So all you need to do is to sum up again along forces along X. So look at the forces along X. Sum up algebraically. We understand that T is negative. It should be added by W, which is positive. Okay? But WB is must be times G. So it is coming from the free body diagram. Okay? Then another thing that Under definition of, if you sum up all forces along X, again, it is the same as the net external force of mass B. Look at the free body diagram. That's why we assign forces, the X-axis downward, to ensure that the sum of all forces along X must be the net external force on mass B. And take note that the net external force using the second law of Newton, it is the product of the mass B and the acceleration of the object A. And that A, remember, is the same as A in equation 1. Okay? So again, we have two definitions of the unbalanced force along X. Then we can equate the two, which means that the negative T plus mBg, which is coming from the free body diagram, should be equal to the mass A times the acceleration of the particle B. Mass B. Okay? So again, we have variable A and we have variable T. No? Then, call it as equation 2. So there were two variables, but don't worry because in equation 1, we have the same variable. So we can now use the systems of equations. No? But the two equations are simultaneous. No? According to algebra, if two or more equations are simultaneous, then we are allowed to use the elimination or the systems of equations. No? So the systems of equations are we have the methods in finding the solution. We have the elimination, and we have by the matrix or determinants way. Now this is a 2 by 2 matrix. Now we can use the elimination process. No? Now take note in elimination process is because hence there are two variables, then we will eliminate one variable, then solve for the other variable. The best thing to do in algebra to eliminate one of the variable is to add the two equations algebraically, because the moment you add the two variables, you are eliminating T, which is the tension in the cord. One is positive, the other is negative. So if you add that, it will be cancelled out. So in that case, we have only A as the variable. Okay? So combine, di ba? Left and right. So we have in the right side, because T was already cancelled, we have only mass B times the acceleration minus mass A times acceleration. In the opposite side, we have mass B times the acceleration plus mass A times the acceleration. So notice that we have only one variable. No? We can simplify this by combining the common factor. The common factor in the left member is G, while the right member is A. So take the common factor, then solve for A. Divide both sides by mass A plus mass B plus mass A. So therefore, in this case, we have the acceleration B equal to what? The gravitational acceleration times the difference between the mass B and mass A. Then divided by the sum of the two masses, the mass B added by mass A. This is the formula to obtain the acceleration for the Atwood machine. So this formula is called as the acceleration of Atwood machine. This is only applicable for Atwood. And take note that this formula, no, we assume that B is greater than A, or the A is less than B. Meaning, if you use this formula, and you come up with the answer of negative, then the meaning of that is A will not move upward, hence B will move downward, vice versa. Okay? Now, if you come up with a positive result, then it means to say that A will move. It's true that A will move upward while B move downward. Okay? Now, therefore, the only factor to solve for A are the masses. No? If you know the two masses, then very easy to calculate the acceleration. This is now very simple because we have already the formula. Now, if you are solving for T, okay, we know already A. What is the tension in the cord? Suppose you are asked. Then all you need to do is to use equation 1 and equation 2. Then solve T. Now, any of the two. Look at equation 1. If you transpose the term in the left member, the negative MAG to the right member becomes plus. Okay? So T can be what? MA plus the acceleration times acceleration plus the mass A. Sorry, there's a discrepancy on that. Okay, that's correct. Okay? Mass A times the acceleration plus mass A times the gravitational acceleration. So we already know the acceleration, then they can be computed. Or you can use the equation 2 by transforming the equation 2 and solve for t. And we come up with mass B times the acceleration, then due to gravity, then minus mass B times the acceleration of the system. Okay? So that's it, no? Now, again, we can always use this formula in solving the acceleration for the Atwood machine. Okay? Now, suppose we have this as an actual, let us say, a problem. Suppose mass A is 8 kilograms. Look at the problem. Okay? Then mass B is 10 kilograms. Mass B is heavier than mass A. So if you substitute this to the formula that we derived for the acceleration of the Atwood, then the result is 1.09 meter per second. Sorry, that's meter per second squared. Kindly correct the unit because it is the acceleration. Meter per second is for velocity. So please change it to meter per second squared. Okay, so thank you. So because we have the result as positive, what does it mean? The meaning is the 8 kilograms should move upward and the 10 kilograms should move downward. It's very clear. Right? So when you release it, it will move upward, A, and B will be moved downward, or the 10 kilogram will be downward. By how much? By how much? With an acceleration of 1.09. Suppose you are asked, what is the tension? Okay, when it's the tension, then use the formula previously. Then you can solve it. Okay, so since we know the acceleration, can we solve for the unbalanced force of A and B? The answer is yes. Why? Because we have already the acceleration. As I've said, very important to know the acceleration because the acceleration is between, is in between the quantities in physics, in mechanics, between the dynamics and the kinematics. Common point of the quantities is the acceleration. If you know the acceleration, almost everything can be solved. Or if given the acceleration, then you can use the kinematics principle and you can use the dynamics principle. So for any available given data, you can use it. Okay. Now suppose another example is suppose the mass A is 9 kilogram and the mass B is 3 kilogram. Take note that A is now heavier. Okay. Now without looking at the system, use the formula. Then the result is negative. Take note negative. Why? Because 3 is, if you subtract 3 by 9, it's negative. So the whole thing, answer becomes negative. And the answer is negative 4.91. Again, change the unit to meter per second squared. Thank you again. Okay. So, take note that negative. What does it mean? The meaning is, because we use the derived formula, the negative means mass A, which is 9 kilogram this time, will not move upward. Hence, it will move downward. And the mass B, which is 3 kilograms, must move upward. By what amount? In the amount of 4.91 meter per second squared. Take note that it is accelerating. Means the velocity will always keep on changing, increasing and increasing as the time goes on. No? Because the meaning of negative, again, is not decelerating. It is not reducing. The negative, with the use of formula, is the direction of the acceleration because there is always acceleration. It can be zero, it can be non-zero. Okay, and the negative in this case is actually by the use of the formula. Okay, now what will happen if we have the same mass, 5 kilogram and 5 kilogram? Use the formula again. 5 minus 5, 0. So meaning the answer is 0. What's the meaning of that? The meaning is the object is at rest. There's no motion occur on that. Okay, even if they are not balanced, no? If you hold it up, then suppose what A is below B, then when you release it, still at rest. Why? Because the net external force is equal to 0. If you pull the mass B in the left or the 5 kilogram in the left side, right side, pull it down, then object mass A, which is 5 kilogram, will be in upward position and release it, then there is no motion occur. Why? Because the acceleration is 0. That's why this is a good, Atwood is a good device, demonstration to show the constant acceleration. It can be 0 or it can be non-zero. Now, if you exert a force on this, then the object will move with a constant speed. Now, it will rest at a certain point. Why? Because we ignore the friction. It says that we ignore the friction between the rope and the pulley. But remember, friction is always present. So there's a time when it's moving that it will rest. But it will rest, which means that acceleration is 0. So again, you can find the point that the particle will be at a constant velocity or maybe in a rest position. Why? Because the acceleration, in that case, configuration 5 kg and 5 kg, the acceleration is 0, and the net external force on the object is also equal to 0. Now, is this consistent? Is the formula consistent to the freely pulling body? Is the Atwood can be considered as a free pulling body? The answer is no. Why? Because there is a string. There is no falling free fall. That's why the acceleration is less than the 9.81. So even if how heavy is the object, one is very light and the other is very heavy, the acceleration cannot exceed the 9.81 because the maximum acceleration by gravity is only 9.81. Meaning, in an Atwood machine, do not expect that you can provide an acceleration by releasing only by gravity. You can provide 9.81 unless you will exert an external force on the object. Then that's the time. But releasing it freely, then in Atwood machine, it's impossible to have the 9.81. It should be less than. Now the question is, can we produce the acceleration of 9.81 from this setup? Again, the answer is you cannot. But if we remove A, okay, meaning if I equate mass A to be equal to 0, what does it mean? Try to imagine. If I release that board, what will happen to the object? So if I set mass A to be equal to 0, or I will cut the string, then the tendency is, mathematically, when you look at the formula, if you substitute mass A to the formula of the acceleration of the Atwood machine, the result is B will be cancelled out because the next term is 0. So if B can be cancelled out, then acceleration is equal to the acceleration of the system of B is equal to Z. And remember, Z is what? 9.81. That's free fall. Which means that if I remove A and also the string and release it, then it is a freely falling body. And that's the time that acceleration is 9.81. So this result shows us that the Atwood machine is consistent with the theory of free fall. But again, it cannot provide this amount of number if there were two objects in the configuration. Okay, so I think that's all for this. So study hard, study hard. It's the only key to understand is to study. Now, watch all my videos in order to understand the physics problem.